Over the centuries, scientists have solved countless mysteries about the cosmos through careful observation and experimentation. But one of the most enduring mysteries is closest to home. We still have never seen how a solar system like our own is born. Our current model of how planetary systems form is mostly based on extrapolation of data from meteorites and observations of our neighbouring planets. And for the most part, scientists think we've broadly got it right. At least the models we've built seem to make sense. There are, however, stages that have remained somewhat mysterious. Exactly how, when, and where planets form being the big one. But that's about to change. Earlier this year, the James Webb Space Telescope found a baby star, hidden in a cocoon of gas. And amongst that gas and dust, planets are being made. For the first time, we've been able to see the very earliest phases of planetary formation. So not only are we finally getting to the bottom of the puzzle, it could even show us something about how our own solar system's planets came to be. I'm Alex McColgan and you're watching Astrum. Join me today as we unravel the secrets of HOPS 315, consider what its future planetary system might look like, and dive into how this discovery is reframing our understanding of planet formation across the universe. Given that we live on a planet, have visited 7 others in our solar system, and found more than 6,000 beyond that, you'd think that we should have a pretty good idea as to how planets form. Well, unfortunately, that's not necessarily the case. Much of what we know today is thanks to the analysis of meteorites that have landed on Earth and observations we've made of the planets in our own solar system as they are now. The rest of it has been left up to models and simulations. Why? Well, it turns out the earlier stages of star and planetary formation are extremely difficult to see. It all starts with huge molecular clouds made up of dust and gas particles. As they move around, they create thermal pressure, pushing outward on the cloud, but these particles also have to obey the laws of gravity, just like everything else. So they also pull each other and the cloud inward. This push and pull remains in perfect balance for millions of years, keeping the nebula stable. But a nearby cosmic event, for instance the shockwave resulting from a supernova explosion, can suddenly send everything into disarray. If gravity starts pulling this gas cloud inward faster than the pressure of its moving particles can push back, we get a runaway effect, a gravitational collapse. The dust and gas from the outer regions begin raining inward, and as everything gets denser and hotter, it begins to spin faster and faster, speeding up like a figure skater pulling their arms in. A heat gradient forms, with temperatures reaching more than 1000 Kelvin within 1 astronomical unit of the center, and cooling to 400 Kelvin at a distance of 5 astronomical units. Over the next 100,000 years, most of the mass concentrates in the middle of the cloud, eventually forming a protostar. The rest is dispersed outward, forming a protoplanetary disk of swirling dust, a womb for this stellar embryo. It's all this gas and dust that make the stellar formation process so tricky to see. Our telescopes can't peer through it, but as technology has improved over the decades, we have started to catch glimpses. In 2013, a team led by Amelia Stutz turned the attention of the Herschel Space Telescope to the Orion Molecular Cloud Complex, the biggest site of star formation near our solar system. Known as the Herschel-Orion Protostar Survey, or HOPS, it searched the Messier 78 nebula. HOPS found 15 new protostars, each with masses between 1/5 and 2 times that of the Sun. These protostars had never been seen before because their gas envelopes are so cold, heated to just 20 degrees above absolute zero, with the protostars hidden deep inside. This indicates that the star hadn't yet had time to warm the gas, they are young. In fact, Stutz and her team believe they are some of the youngest protostars to ever have been found, finally giving us something to compare our models to. But the initial star formation isn't the only process we know very little about. How planets themselves come to be is just as much of a mystery. Our simulations tell us that in the main body of this disk, the dust and gas particles begin to accrete. They condense into microscopic solids, which clump together into larger and larger grains over millions of years. Eventually, these solidifying clumps of spinning debris become planetesimals, the building blocks of primordial planets spanning several kilometers across. If enough come together, either via gravity or collisions, they can form a planet. The problem is, we've never seen most of this happen. We've found young planets. This one is 4 times the mass of Jupiter and less than 5 million years old. And this gas giant is even younger. Its star is only 2 million years old. But that's as early as it gets, and they are already fully formed objects. There's hundreds of thousands, if not millions of years gap to fill in. That is, until now. 1,300 light years away, in that Orion Nebula, a baby solar system is being born, and we're watching it with our own eyes. Well, James Webb's lens. This is HOPS 315, a star that's less than 150,000 years old and 0.6 solar masses. It's still growing, feeding on an envelope of dust and gas that hides in a cloudy veil. But incredibly, researchers found a gap in the clouds and managed to snap a photo. And they saw something extraordinary. Webb's infrared spectra showed the presence of both warm silicon monoxide gas and tiny silica crystals near the young star. We were witnessing the moment gas condenses into a solid for the first time. This is a big deal because as a protoplanetary disk starts to cool, compounds begin crystallizing in a specific order based on their condensation temperatures. This is known as a condensation sequence. We can infer this sequence from our understanding of chemistry and our analyses of primordial asteroids, which are like time capsules of our early solar system. The oldest condensates trapped in these asteroids are calcium aluminium inclusions, or CAIs, and crystalline silicate materials. The fact that we saw both silicon monoxide gas and solid crystalline silicates around HOPS 315 indicates that this star and its system are at the very beginning of their formation. In other words, we were watching the very first stage of planet formation as it's happening for the very first time. This was a major breakthrough, and as lead author of the landmark paper, Melissa McClure puts it, for the first time, we've identified the earliest moment when planet formation is initiated around a star other than our Sun. They wanted to explore further, so Professors Melissa McClure and Merrill Van 't Hoff focused the Atacama Large Millimeter Submillimeter Array Telescope, or ALMA, on this baby star. Whilst James Webb Space Telescope revealed the warm inner regions of a young star through infrared light, ALMA specializes in observing much colder material, the dust and gas that emit millimeter and submillimeter wavelengths of electromagnetic radiation. This allows astronomers to trace the chemical composition and structure of molecular clouds. By combining the two observatories, McClure and Van 't Hoff could connect the dots. James Webb found the evidence of early planetary formation, and ALMA pinpointed where in the disk that process was taking place. What's most interesting about this is that it's roughly in the same region around HOPS 315 as asteroids made of similar materials are found around our Sun. We don't know exactly what this means yet, but it suggests that the same early building steps for planets may happen in many young systems, and there's more. It's worth mentioning that although silicates were found, the outflow jet they studied is actually suspiciously low in silicon, the most important element for making silicates and therefore planets. There's just 2% of what McClure expected relative to the amount of carbon they found. But this isn't a bad thing for planet formation. McClure says that may be a hint that planetesimals are already forming there in a similar way that they must have in our solar system. An intriguing finding given the system is so young. We are finally able to timestamp the beginnings of planetary formation to less than 150,000 years after a star begins to form, which is turning our models on their heads. Initially we thought gases only began condensing once the central star formed a Class II system, or when the stellar envelope is mostly gone, the star has stopped growing, and what remains is a relatively calm, well-behaved debris disk. But over the last decade, mounting evidence from several young protostars, like these, have suggested that planet formation actually starts way earlier. Still, these disks were not well categorized. HOPS 315 has gone one better and confirmed our suspicion. But there's still one mystery about the nebula hypothesis. Scientists have long struggled to explain how millimeter-sized chondrules grow into rocks kilometers in diameter. Small particles don't naturally stick together, and medium-sized objects fall into the star within about 100 years due to gas drag. One proposal is that dust collapses in pockets of gravitational instability, directly forming planetesimals, a rock emerging from a sandstorm. By repeatedly observing how the gas-to-solid ratio changes in HOPS 315, scientists can uncover how fast solids grow within the inner disk, what might limit their coalescence, and how that affects planet development. But perhaps most impactful of all, the HOPS 315 system is one of the best that we know to actually probe some of the processes that happen in our solar system. By comparing HOPS 315's dust chemistry with meteorites from Earth, scientists can see whether the same condensation sequences and elemental distributions that shaped our planets occur in other parts of the universe. We can finally test our models against the real thing. But just as with anything in science, as soon as you make a discovery, it leads to many questions. So, what's next for HOPS 315? How many planets will it have? Will they be split into small, rocky planets in the inner solar system and icy gas giants in the outer reaches of the star's influence? Well, the condensation sequence in the protoplanetary disk has a direct impact on what kinds of planets form and where. This lets us at least make an educated guess. Since the early disk isn't uniform in temperature, different compounds will condense first in different parts. One feature of this is called the snow line, the point beyond which conditions allow ices to form. In our early solar system, this line was at about 2.7 astronomical units for water ice. Beyond this snow line, ice and dust accumulate, slowly snowballing into giant planetary cores. The colder temperatures out here also mean gas travels slow enough to be captured by the growing gravity of these frozen cores. Eventually, enough gas is captured to form a planet, and a gas giant is born. This process happens very fast. We think it's how Jupiter and Saturn formed in as little as 10 million years. Meanwhile, on the other side of the snow line, ice and volatiles are completely vaporized. Here, only materials with very high melting points like iron, nickel, aluminium, and rocky silicates survive. By now, most of the gas in the system has been captured, either by the growing star or the gas giants, meaning there's almost none left for these longer gestating worlds. The result is smaller, rocky planets like the ones we see in our inner solar system, including Earth. We don't know how many planets will form around HOPS 315, but we'd expect to see a similar setup to our own solar system, with inner rocky worlds and outer gas giants, although we still can't rule out planetary migration and hot Jupiters. Given that the current beginnings of planet formation are happening at the approximate location of our asteroid belt, one question is whether HOPS 315 will have one. Ours sits between 2.2 to 3.2 astronomical units from the Sun, and we've already established that asteroid belts aren't a feature unique to us. In 2001, researchers found the first asteroid belt outside of our solar system, 70 light years away around Zeta Leporis, a star 1,000 times older than HOPS 315. But whether one develops around this baby star depends on a few factors. We have our asteroid belt thanks to Jupiter. Initially, the region between Mars and Jupiter was full of dust and planetesimals. There was plenty of material to form another planet. But once Jupiter formed, it got massive fast, and that strong gravitational pull and orbital resonances disrupted the surrounding region, halting accretion and trapping planetesimals in stable orbits around the Sun. This left behind a population of primordial space rubble that never coalesced into a planet, instead becoming the asteroid belt we know today. So one way for HOPS 315 to end up with an asteroid belt is for it to create a planet with enough mass to cause a gravitational disturbance like Jupiter did. But if a large enough planet never forms, HOPS 315 could end up with an intermediate world around the snow line, something our own solar system never developed. So HOPS 315 is a portal to our past. Studying it is like looking at our own solar system 4.6 billion years ago, when Earth was still a dispersion of gas and dust. But its discovery also raises big questions. How common are solar systems like ours? Does planet formation always start at 2.2 astronomical units? How fast does the disk go from microscopic dust to planetesimals? To answer these questions, researchers are eager to start expanding the search to more very young stars to see if they can spot any others like HOPS 315. If multiple systems show the same hallmarks of creation, we'll have found a protoplanetary goldmine, a wealth of observations and data to pore over to better understand our origins. Whatever they find, one thing is for sure. We were once a swirling cloud of dust, and billions of years from now, we'll be dust again. So perhaps, while we're here, we should make the most of it. Think you know Jupiter? Think again. For decades, scientists argued over what the core of our biggest gas giant was like. Was it solid or missing altogether? Then, in 2017, NASA's Juno mission made that debate irrelevant overnight. The data from Juno suggested both sides were wrong, and revealed a third option no one expected. Jupiter's core isn't solid, but it isn't absent either. It's fuzzy. And that's a problem, because it upends everything we thought we knew about Jupiter's formation, its interior, and even its bizarre magnetic field. I'm Alex McColgan, and you're watching Astrum. Join me today as we uncover exactly what Juno found, explore how a fuzzy core could form in the first place, and reveal why this changes how we think not just about Jupiter, but gas giant planets everywhere. For decades, two competing theories dominated the scientific conversation around Jupiter's core. Many supported the gravitational collapse theory, which suggests that Jupiter formed directly from the collapse of a gas cloud under its own gravity. This would have happened in the colder, outer reaches of the solar system before Jupiter migrated to its current location. In this scenario, the gas giant would have no core at all. It would simply be a layer cake of churning gas all the way through. But this theory didn't have the whole scientific community convinced. Others were almost certain Jupiter's core was solid, made up of heavy elements like carbon, nitrogen, oxygen, magnesium, silicon, and iron. As this solid core grew larger and larger, its gravity started capturing more hydrogen and helium, swirling it together over millions of years to form the planet we all recognize today. Intuitively, this seems to make sense. Our solar system formation models suggest giant planets could be created this way, since ice and rock would condense first in the outer solar nebula, capturing gases in their gravity as they migrated inward. This theory, known as the core accretion model, predicted a dense, well-defined core with a clear boundary separating the compact center from the surrounding layers of gas. To resolve the debate, early missions to Jupiter all took their turn trying to discern what lies beneath the red giant's dramatic atmosphere. By the 1990s, scientists knew that Jupiter was rich in heavy elements, implying the planet was made of more than just hydrogen and helium. The Galileo mission also found evidence that Jupiter's magnetic field must somehow be generated by liquid, metallic hydrogen in its interior. But if the core is purely liquid, how did Jupiter form in the first place? The standard theory of planetary formation requires a solid nucleus to start gas capture. If Jupiter once had such a core, but somehow lost it, how did that happen? Could everything we know about how gas giants form be completely misguided? Despite the successful missions to Jupiter, the planet's structure remained a mystery. The data gathered wasn't precise enough to determine whether its core was solid or diffuse, what it's made of, or how exactly it generates such a massive magnetic field. But that all changed with Juno. On the 5th of August 2011, NASA's Juno mission launched from Cape Canaveral in Florida. Its main objective was to get closer to the truth of Jupiter's composition by measuring its gravitational and magnetic fields with unprecedented precision. Unlike Galileo, Juno was purpose-built to map the planet's gravitational field in great detail, about 100 times better than previous maps. When it entered orbit on the 4th of July 2016, it began tracing a highly elliptical polar orbit, swooping down within just 4,200 kilometers of Jupiter's cloud tops. It did this again and again from several angles, a path that made this probe incredibly sensitive to tiny changes in Jupiter's gravity. But why are we interested in gravity in the first place? What does that have to do with figuring out what Jupiter's core is made of? Well, we've all seen gravity depicted like this, a perfectly round cone, the same on all sides. I'm sorry to tell you, this diagram is a bit of an oversimplification. For a planet's gravity to be completely uniform like this, the distribution of mass inside it would also have to be perfectly uniform. In reality, if you zoom in really close, their gravitational fields look a little more like this. Planets are made up of many different elements and materials, each with their own masses, densities, and distributions. These differences are reflected as tiny, almost imperceptible variations in a planet's gravitational field. That's why Earth's gravitational field is actually slightly different over mountains than plains, and why scientists are so fixated on mapping Jupiter's gravitational field with incredible precision. As Jupiter's gravity fluctuates, it causes Juno to speed up or slow down. This spacecraft is so precise, it can detect changes in speed as subtle as 0.01 millimeter per second. At the same time, Juno is continuously beaming a steady radio signal back to Earth, which scientists can decode using the Doppler effect. Where gravity is stronger, Juno accelerates, and we perceive a higher frequency wave, while a deceleration due to weaker gravity would result in a lower frequency wave. By repeating this over and over, scientists can build up a very precise map of Jupiter's gravitational field, which directly reflects how its mass is arranged inside. While the Galileo mission managed to paint Jupiter's gravity in very broad strokes, Juno brought it into razor-sharp focus. And what it revealed about Jupiter's core caught researchers by surprise. Turns out, both theories about Jupiter's core were wrong. It seems to have a core, but it isn't solid like we thought. It's fuzzy. Instead of a dense, compact ball, it's dilute, gradually blending with the hydrogen-rich layers above it. It doesn't appear to have any sharp boundaries. It's also much wider than expected, spanning about half the radius of Jupiter itself. The findings quickly sparked a flurry of questions, including whether our understanding of how Jupiter formed needed a refresh in light of this exciting new data from Juno. A popular theory soon emerged to explain this unexpected discovery, that Jupiter once had a solid core to begin with, but a catastrophic collision in its early history shattered and scrambled it in with the surrounding lighter gases to give us the fuzzy core we see today. The only problem is, our standard model for how giant planets like Jupiter form doesn't work without a solid core. So either Jupiter's fuzziness somehow developed later on, or our models are wrong. Anyway, for such a dramatic shattering to occur, the collision must have been massive, possibly with another young planet. Scientists speculate that up to half of Jupiter's core could have originated from the remains of this planet. It was a neat enough theory, except for one unexpected hiccup. A curious team of researchers tried to model this giant collision using a supercomputer. They wanted to emulate the exact event that would lead to the results Juno showed us. So they designed several possible scenarios of a massive object colliding with a Jupiter-sized planet and ran multiple simulations, varying the size of the Jupiter protoplanet and the angle and speed of collision. But try as they might, they couldn't find an event that led to the fuzzy core Juno showed us. Every time they tried, the models did the same thing. The impact would initially rock the planet to its core, but after a while, the dense, rocky material would settle back down again, like sediment at the bottom of a glass. It didn't dissolve into the rest of the planet. A sharp boundary would reappear, clearly separating the core from the outer hydrogen layers. It didn't fit the Juno data, so it was back to the drawing board. Funnily enough, the next clue in this puzzle didn't come from Jupiter at all. It came from its next door neighbor. Well, that is if you consider 648 million kilometers away next door. We've known since 2014 that the waves in Saturn's rings are caused by vibrations inside the planet. This gives us an insight into what the planet's core might look like, similar to how earthquakes let us study Earth's interior. When researchers paired Cassini's gravitational field data with these wave measurements, it painted a staggering picture. These observations show that at least some of Saturn's deep interior doesn't convect. This is a big deal. Inside a giant planet like Saturn, heat is constantly trying to escape. Normally, that happens through convection. It's what is constantly happening in Earth's mantle, or when you heat up a soup. Hot fluids rise to the surface, cool, and then fall back down, only to be heated up and rise again. On and on it goes. If Saturn were fully convective, it would mix heavy elements throughout its interior. There wouldn't be a dense central region at all. The whole thing would be a fully mixed, homogeneous soup. But if it were partly stable against convection, we'd expect to see a gradient of material, with heavier elements concentrated towards the center and tapering outward. And that's exactly what the data shows. Researchers published their findings in 2021, arguing that the only way to explain Saturn's ring wave data, gravitational field data, and partial lack of convection is that it too has a fuzzy core. As it happens, Juno data also suggests large regions of Jupiter may not be convective. We seem to be slowly connecting the dots. If Saturn and Jupiter have fuzzy cores, they likely stem from a common denominator rather than a random collision event. Now, scientists are working on a new, emerging theory of how the gas giants came to be, one in which fuzzy cores are a natural part of planetary formation. We haven't arrived at a neat explanation yet, but it is clear that the old assumptions we had about the largest planets in our solar system are incorrect. Jupiter and Saturn are not made up of solid core and gas envelope, nor do they have a completely mixed interior. Their fuzzy cores are made up of a compositional gradient, with more heavy elements concentrated in the center, which dissolve out into the gas envelope without a clear boundary. This complexity and uneven mixing challenges our current models for planetary evolution. Where our old, simplistic model predicted the giants would cool predictably over time, these new models don't follow the same patterns. And the same is true for all the gas giant exoplanets we've discovered and studied so far. But in the meantime, there is one other jigsaw piece that needs to fit the puzzle created by Jupiter's fuzzy core: its weird and wacky magnetic field. For years, scientists have known that Jupiter's magnetic field is generated through a dynamo process in its metallic hydrogen layer. This layer spans 20 to 60,000 kilometers deep, where temperatures can exceed 30,000 Kelvin and pressures are millions of degrees greater than on Earth's surface. Under these extreme conditions, hydrogen is in a liquid state, but even more incredibly, here, hydrogen's electrons become delocalized or free-flowing. This creates an electrically conductive metallic state. Coupled with Jupiter's fast rotation, this metallic liquid hydrogen creates a dynamo effect, though the exact process of how it's powered remains a mystery. Whatever it's doing, it's working. Jupiter has the largest, strongest magnetic field of any planet in the whole solar system. Its magnetosphere spreads 7 to 21 times the diameter of Jupiter, tapering into a tadpole shape behind it that extends into Saturn's orbit, about 1 billion kilometers away. However, Jupiter's magnetic field also has some quirky characteristics. It's much stronger in the northern hemisphere than the southern hemisphere, has intense, localized magnetic spots, and 2 magnetic south poles. Scientists hoped Jupiter's fuzzy core might actually explain some of these strange behaviors. Frustratingly for them, the opposite turned out to be true. Jupiter's fuzzy core actually complicates rather than explains its magnetic field. Magnetic fields in planets are usually created by swirling motions of electrically conducting material, like the metallic liquid hydrogen in Jupiter's core. However, Juno data showed that large regions of Jupiter, like Saturn, seem to be at least partially non-convective. Researchers modeled the fluid dynamics of Jupiter's interior in 2 potentially non-convective regions to see how they would affect the magnetic field, one in the upper part of the planet's interior and the other lower down, corresponding to the dilute core. They concluded that the upper stable layer helps explain Jupiter's magnetic field even better than previous solid core models. However, the lower region, representing the non-convective dilute core, did not explain Jupiter's magnetic field on its own. In other words, a completely stable fuzzy core produces a magnetic field that's very different from the one we actually observe. Now, researchers believe Jupiter's dynamo is more complicated than originally thought. It's possible that below the uppermost molecular hydrogen layer, Jupiter has a layer of helium, which rains down through the liquid hydrogen, like oil passing through water. Some think this could have an effect on the magnetic field. Another theory claims Jupiter's dynamo doesn't operate in a homogeneous way like it does on Earth, and that instead, the planet's lopsided magnetosphere is the result of variations in density, electroconductivity, or both. But on the whole, no one knows exactly how this magnetic field is produced, or what role the fuzzy core plays in its creation. One thing we do know for certain though, is Jupiter's magnetic field is responsible for the biggest, brightest auroras in the solar system. On Earth, auroras are only visible for a 4 to 6 month window. On Jupiter, they never stop, covering the poles with a dazzling display of colour hundreds of times more powerful and energetic than the auroras we're familiar with. By stringing together far UV images from Hubble's imaging spectrograph, scientists were able to create these videos of the auroras in action. Aren't they spectacular? Despite Juno's discoveries, Jupiter keeps its secrets close to its chest. We still don't know how its fuzzy core actually formed, nor do we know how permanent it is. Is the fuzzy core a stable structure that will endure for billions of years? Or is it slowly dissolving into Jupiter's gaseous layers? What relation does it have to the metallic hydrogen above it? And the resulting magnetic field Juno mapped? Are fuzzy cores just a natural part of gas giant formation? We can't say for certain yet. But one thing's for sure, our current models don't show the full picture. Hopefully with further study, we'll slowly be able to answer these questions one by one. Though, the more we learn, the more questions we'll keep asking. The pursuit of truth is relentless, and it is also perhaps the most human thing we can do. When we look out into the vast, expansive, awe-inspiring cosmos, there are innumerable stars out there. Yet, one of them dominates our sky and our lives, burning brightly and ferociously at the center of our solar system, the Sun. It's easy to see how generations of humans before us were inspired to create all kinds of legends to explain its mesmerizing glow. Now, as technology has advanced beyond the realms of their wildest imaginations, we can delve into the processes within and around our neighboring yellow dwarf, going deeper than ever before. As we journey through its ferocious atmosphere, let's explore what I'm sure you'll agree are the fascinating phenomena that materialize there. I'm Alex McColgan and you're watching Astrum, and in this video I want to dive into the Sun, drawing on different wavelengths of electromagnetic energy to showcase the star in a new light. Previously, we've explored Jupiter and some of its moons through the lens of the electromagnetic spectrum, which you can see in this video here. Today, we will be revisiting this approach, but this time, rather than a planet, it'll be adapted to investigate a highly energetic ball of plasma. The light we'll be looking at is old. Although light is the fastest thing we know, the image of the Sun that we see from Earth is approximately 8 minutes and 20 seconds old, meaning we are viewing what the Sun looked like a few minutes in the past. And if you count how long it takes the photons generated within the Sun's core to make their way through each layer of the Sun before escaping into space, the light that reaches us is anywhere from 10,000 to 170,000 years old. Where to begin? Like eating a fruit by starting with the outer layers and working your way in, let's start our investigation with the outermost layer of the Sun's atmosphere, the corona. The following image was taken by the Solar Dynamics Observatory, or SDO, a NASA space mission launched back in February 2010. SDO aimed to better understand the solar variations that influence life on Earth and our technological systems by studying the dynamic solar surface and atmosphere at different electromagnetic wavelengths. By looking at light beyond the visible range, NASA was able to pick out normally invisible details crucial to our understanding of the Sun. This image was taken using a 19.3 nanometer wavelength, representing light found in the extreme ultraviolet region. At a wavelength corresponding to a color temperature of 1 million Kelvin, we can clearly see the higher region of the Sun's corona. Interestingly, the Sun's corona can also be seen by the naked eye on rare occasions, such as during a total solar eclipse. When the moon is perfectly aligned between the Earth and the Sun for a fleeting period of time, the view of the central, brighter disk, known as the photosphere, is fully blocked, revealing a radiant exterior. While this is a breathtaking view already, the corona is still nowhere near as detailed as it is in this image taken by the SDO. This makes it a useful tool for scientists' studies. But let's go a little deeper, to features of the Sun just beneath the corona. At a color temperature of 20 million Kelvin, the intensely vivid spots indicate events known as solar flares. Here is some footage of a particularly busy week for flares back in August 2022. I've always found solar flares to be both terrifying and hypnotizing. They are colossal explosions where the Sun spews out an immense amount of electromagnetic radiation. They are caused when magnetic fields cross, distort, and reorganize themselves rapidly. This activity is created by the turbulent nature of the plasma within the Sun itself, from which the fields ultimately originate. But they are not the only feature of the Sun's atmosphere venting radiation. Coronal holes, indicated here by this darker region on the Sun, are another fascinating feature which we'll take a closer look at using extreme ultraviolet light. Coronal holes are areas of cooler, less dense plasma which are magnetically open, meaning that rather than forming closed loops that go back to the Sun's surface, the field lines travel outward across the solar system. These areas allow solar wind particles to escape more easily into space. When these solar winds are directed towards and collide with Earth's magnetosphere, beautiful auroral lights dance across the night sky at the Earth's polar regions. Using ultraviolet light gives us a much better view of these fascinating features of the Sun's outer layers. Non-visible spectrum light is an incredible tool, and there are so many different features in the Sun's outer layers to look at. There are solar filaments, known as solar prominences, the large loops of plasma that rise from the Sun's surface. These enormous loops are large enough to make the Earth look like a tiny speck and can stretch hundreds of thousands of kilometers into space. They can form in as little time as a day, but a stable prominence can remain in the corona for several months. In this example, we watch as a solar prominence snakes its way out of the photosphere and into the Sun's atmosphere. Although this video is sped up so the minutes seem like seconds, when you consider the size of the prominence, it becomes clear how swiftly the Sun's intense magnetic fields are causing this material to move. One fact you might not know about the Sun's atmosphere is that it sometimes rains there. Not all of the charged plasma fired into the Sun's corona continues out across the solar system. Some remains in the corona, getting trapped and cooled until it falls back to the Sun's surface as a shining rain. This coronal rain is beautiful to look at, but is best observed from a distance. It's still millions of degrees in temperature. Of course, falling gently back to the Sun's surface is only the fate of some of the Sun's plasma. This is where the comparison to Earth fails. After all, on Earth, the clouds do not crack like a released elastic band firing into space. On the Sun, thanks to tightly wound magnetic fields, they do. This is a time-lapse of a coronal mass ejection. Watch as the structure forms at the bottom left of the Sun for some time, before eventually snapping and sending billions of tons of plasma out across the solar system. Even with the Earth's magnetic field, being hit by a powerful one of these could be devastating for our satellites and electrical grids. All these structures are imaged by the SDO here utilizing a 30 nanometer wavelength of light, which corresponds to the extreme ultraviolet portion of the electromagnetic spectrum. Timing is important when trying to image these features, as they are more common in certain years than in others. In fact, each structure is dependent on the solar activity of the Sun, alternating around an 11-year solar cycle, which I did a video about here. But there's more to learn. Just as using visible and ultraviolet light shows us different things when looking at the same feature, using two different wavelengths of non-visible light can also be eye-opening. To demonstrate this, take a look at these two images of the Sun's corona. Taken over the same time period, the following two images use different wavelengths of light. The first, imaged at a color temperature of 600,000 Kelvin, depicts the quiet corona and features coronal loops. The second, imaged at a color temperature of 2 million Kelvin, displays the much hotter active regions of the corona. The stark comparison between the two images highlights the importance of using different approaches when investigating the star. What may initially appear to be a singular solar phenomenon can be revealed as a complex, intertwined chain of events, and we still haven't technically made it through the Sun's atmosphere yet. Moving further inwards, let's look at another image produced by the SDO utilizing a 160 nanometer wavelength of light, this time of the transition region. The transition region is a layer which sits between the Sun's corona and the chromosphere, the lowest layer of the Sun's atmosphere. It's a very shallow layer, approximately 100 kilometers in thickness. In this region, the thermal temperature of the Sun rises dramatically from around 8,000 to 500,000 Kelvin. For an earthly comparison, fiercely scalding lava erupting in Hawaii is 1,170 degrees Celsius or 1,443 Kelvin. The temperature at the lower, deeper end of the transition region is almost 6 times hotter than this. At the upper end of the transition region, the temperature is more than 346 times hotter. Traveling even deeper, we find ourselves immersed in the Sun's chromosphere, which is the last layer of atmosphere before we reach the Sun's surface itself. Imaged here, using 170 nanometer ultraviolet light, it is estimated to be approximately 1,700 kilometers thick. Closely inspecting the chromosphere, we identify some mesmerizing features known as spicules. Swaying like long, wavy grass blowing in the wind, these long jets of plasma shoot upwards from the Sun's surface at speeds up to 100 kilometers per second, approximately 282 times faster than the speed of sound, and can reach lengths of nearly 10 kilometers, over 1 kilometer taller than Mount Everest. Forming and vanishing in around 5 to 10 minutes on average, the processes behind these spicules were widely unknown and debated for some time, as it wasn't clear how magnetically charged particles could ever escape the Sun's magnetic fields at that level. That is, until 2017, when a team of scientists working on an extremely detailed model of the spicules discovered that their origins must be related to neutral particles. Scientists had not originally included neutral particles in their models of the Sun, as they didn't think they affected the motion of the magnetically charged particles. But once they were added, it transpired that the neutral particles gave the magnetically charged particles unexpected buoyancy they needed to escape the Sun's plasma and shoot up into spicules. Descending further through the Sun's lower atmosphere, we eventually reach the photosphere, the surface of the Sun itself, which is best imaged using visible light. While the edge of the photosphere appears sharp and precise, as it often does to our naked eye, this is simply due to how far away the Sun is. The Sun itself is not solid at all. Since it is too hot for matter to exist in a solid, liquid, or gas state in any region of the Sun, it can only be plasma, referred to as the fourth state of matter, and is estimated to make up 99.9% of all the matter in the universe. Plasmas tend to behave a lot like gases, except they are made up of a mixture of ionized atoms and free electrons. The photosphere is the outermost layer in this image, around 400 kilometers thick. It is not a fixed, solid boundary of the Sun, unlike what this image may suggest. And sadly, it is the deepest layer of the star which scientists can measure directly. At a closer look, you may notice some dark spots on the left-hand side. These are known as sunspots and appear darker than other parts of the photosphere due to their cooler temperatures. But that's only in comparison to their scorching hot surroundings. Unlike coronal holes, sunspots form in areas where magnetic fields are particularly powerful. Here, heat becomes trapped beneath the photosphere due to decreased convection within these areas. When comparing this image of the Sun to a previous one taken using extreme ultraviolet light over the same period, a connection between sunspots and solar flares emerges. The captivating solar flares and sunspots coincide at the same location. From peering beneath the surface, it becomes clear that one must lead to the other. Now, let's take a closer look at some similar sunspots. This image was taken using the Swedish Solar Telescope, based here on Earth. and using a wavelength of visible light of approximately 400 nanometers. Next to and surrounding the sunspots, the photosphere is saturated with these jagged-edged, endlessly shape-shifting cells, which doesn't look dissimilar to lava as it cools and cracks. However, these cells are around 1,000 kilometers wide and are known as solar granules. Consider them from the top layer of a churning convection cell underneath. Brighter areas inside each granule represent fluid of unimaginable temperatures rising from within the sun's upper interior layer to its surface. Upon reaching this boundary, the fluid has nowhere to go except to spread outwards and across. After cooling gradually, the fluid sinks back inwards via the rough, dark boundaries surrounding each cell, before repeating the cycle. This process closely resembles the convection currents within the Earth's mantle, responsible for driving plate tectonics. This process is no joke. While on average it is estimated that each granule lasts for as little as 20 minutes, the flow within the cells reaches supersonic speeds of more than 7 kilometers per second, generating waves on the sun's surface due to sonic booms. Fascinatingly, these granules can also be seen in the full disk view we saw earlier, utilizing the same wavelength of visible light. You may think this image looks quite grainy for such a high-tech space probe, and you're right, it does. But that graininess is the granules on the photosphere of the sun, not a processing effect or excess noise in the image. And that's it. Sadly, our journey ends here, as scientists have not yet figured out how to image deeper into the sun, using either visible or non-visible light. Much of what lies beyond this layer remains shrouded in mystery, but we can see the benefits of using light of all different spectrums in our study of the sun. They help us observe exploding solar flares, vast coronal holes, swaying spicules, intriguing sunspots, and shape-shifting cells, just to name a few, in completely new ways. The sun is abuzz with lively activity, and so much of it would be invisible to us were it not for these imaging techniques. Maybe one day we'll find ways to see deeper, using techniques we can barely dream of currently, just like those ancient generations of humans long ago could hardly dream of the methods we're utilizing these days. But for now, just knowing there is so much going on unseen in the universe, and knowing we have the means to uncover it, fills me with excitement and curiosity. Who knows what else might be out there, waiting to be found. Supernovae are full of mystery. We still don't fully understand what makes them explode. That's partly because they're impossible to predict. We know what type of star is said to detonate, but have no way of knowing exactly when. In fact, most of the data we have about these spectacular events comes from studying their remnants, in many cases hundreds, if not thousands of years after they began. That or a stroke of dumb luck, where we just happen to be looking in the right direction at the right time. But earlier last year, this changed. We finally captured a supernova as it was exploding, and on purpose. Finding it just hours after it began, this is one of the earliest detections we've ever made, and it's shown us something we've never seen before: the shape of the explosion. It might sound like an unusual thing to get excited about, but this discovery has the power to unlock the inner workings of exploding stars and answer centuries-old conundrums. What are the mysterious mechanisms that drive a supernova? How does a core collapse inward, then suddenly explode outward? And why do some supernovae fail? Thanks to new data from the Atlas survey, we're edging closer to answers. I'm Alex McColgan, and you're watching Astrum. Join me today as we watch a star explode in real time, decode the shape of its blast, and find out what really happens in those critical seconds before a star rips itself apart. On the night of the 10th of April 2024, the Atlas survey was conducting a routine sweep of the cosmos. It consists of 4 wide-field telescopes positioned around the globe in South Africa, Chile, and 2 in Hawaii. Together, they systematically scan the entire night sky every 48 hours, imaging each region 4 times in that window. This rapid revisit time helps catch fast-moving events as they happen, and at 3:21 a.m. on the 11th of April, that's exactly what happened. Atlas detected something unusual. A single point in the sky, brightening dramatically over the previous 5.8 hours. Immediately, this reading triggered the telescope's automated alert system. The news of the unknown transient spread to the astronomical community across the world, who quickly got to work deciphering what it could mean. 23.8 million light-years away, in the spiral galaxy NGC 3621, a star had just died. What Atlas caught was a Type 2 supernova, right as it happened. Yi Yang from the Tsinghua University in Beijing and his colleagues knew what this meant. It was their chance to see, for the first time, the true shape of a supernova explosion in real time. But they had no time to waste. In addition to being impossible to predict, the initial breakout period of a supernova explosion is incredibly short-lived. Once they go off, their original geometry remains intact for just hours. After that, the ejected material crashes into surrounding gas and dust, warping and obscuring the blast's original shape. The pristine fingerprint of the core collapse, the very thing needed to understand how massive stars die, would be gone forever. So to get a true reading, the researchers had to act fast. While most of the world slept, Yang and his team worked through the night, drafting an emergency proposal to the European Southern Observatory. They urgently needed time on one of the most powerful instruments on Earth, the Very Large Telescope in Chile. If they were going to measure the shape of the explosion, they had to start gathering data right away. Luckily, ESO immediately approved the request, and the VLT swung towards Galaxy NGC 3621. Yang and his team waited, with their hearts in their throats and their eyes locked on their screens. This was the moment of truth. Had they taken too long? Would they get a pure reading back, or a scrambled mess of inputs from an already warped explosion? By the slimmest of margins, they'd pulled it off. Precious data started streaming in, painting a picture of true, undistorted supernova geometry. Yang and his team were witnessing the birth cry of Supernova 2024 GGI, and learning at last how the universe makes its most violent fireworks. Supernovae come in 2 main types, but we'll focus on type 2 here, the kind Yang and his team observed. Through a mix of physical theories, astronomical observations, and computer simulations, we've managed to build a pretty respectable model of how we think stars die. Stars spend their lives fusing lighter elements into heavier ones by combining nuclei into more tightly bound configurations. This fusion process releases excess energy, creating an outward pressure that pushes back against the star's own gravity. This keeps the star in a stable, spherical shape. Over billions of years, the star's core works its way up the periodic table, fusing hydrogen into helium, helium into carbon, carbon into oxygen, neon, magnesium, silicon, and finally, iron. But this is where the chain stops. If you want to fuse iron into something heavier, that reaction won't release energy. It will require an energy input instead. Iron 56 has the lowest mass per nucleon out of every possible nuclear configuration, so every chain of nuclear reactions will ultimately turn every other type of nucleus into iron 56. Eventually, the star's entire core becomes iron. It's a dead end. With no more energy releasing fusion reactions available, the star has run out of fuel. It stops burning. The outward pressure that has been holding it up against its own gravity disappears. Without that support, the core collapses on itself at breakneck speeds. The outer part of the core can reach velocities of 70,000 kilometers per second. That's 23% the speed of light. The collapse is so violent that it crushes protons and electrons in the inner core into neutrons. It also releases a flood of neutrinos, nearly massless particles that carry away enormous amounts of energy. The collapsing material slams into the newly formed neutron core and rebounds, creating a shockwave that propagates outward at thousands of kilometers per second, a process known as core bounce. But the shockwave doesn't make it far. Within milliseconds, it stalls nearly 100 to 200 kilometers from the center as it plows through the dense outer iron core. The extreme temperatures and pressures tear apart the heavy iron nuclei back into lighter elements like helium, a process that absorbs enormous amounts of energy from the shock. This is the moment where one of two things can happen. If the shock stays stalled for more than about a second, the star will keep accreting mass until it collapses into a black hole. There's no bang, no brilliant burst. Everything slips into the void. A failed supernova. The more common and mysterious alternative is that the shock doesn't stall, it gets revived. Something, neutrinos, jets, magnetic fields, or some combination we don't yet understand, transfers enough energy to allow the shockwave to continue and turn the implosion into an explosion. Exactly how this happens remains one of the biggest unsolved mysteries in astrophysics, and is why events like SN 2024 GGI are so tantalizing to the scientific community. The shockwave travels up through thousands of kilometers of stellar material. The journey takes several hours until finally it breaks through the outermost layer of the dying star. This is the breakout phase. As it emerges, the shockwave creates a brilliant flash of ultraviolet and optical light, releasing huge amounts of energy and heating the star's outer layers to tens of thousands of degrees. It's only at this point that the supernova becomes visible for the first time, reaching peak brightness over the next week or two. And the beginning of this rising brightness is exactly what Atlas saw in the early morning hours of the 11th of April 2024. Atlas catching SN 2024 GGI as early as it did was a triumph. But detection was only the opening move. The real work began after the alert went out, a race against the clock to put the right instruments on target before the explosion's original geometry vanished forever. That urgency was exactly why Yang and his team had fought for time on the VLT. They weren't just trying to see the supernova, they were after a very specific signature hidden in its light, something only one instrument could reveal. Mounted on the VLT is an instrument called FORS 2, the only one of its kind in the southern hemisphere. It measures spectropolarimetry, how light is polarized across different wavelengths of the visible spectrum. Normally, light waves vibrate in all directions perpendicular to their direction of travel. This is unpolarized light. But polarized light has waves that only vibrate in one direction. For example, when sunlight reflects off a flat surface like water or glass, it becomes partially polarized. It's also why, when you put on polarized sunglasses, this glare disappears. They're designed to filter out that kind of polarized light. In the context of SN 2024 GGI, Yang was interested in polarized light because of what it could reveal about the shape of the explosion. A perfectly spherical explosion scatters light equally in all directions, producing no polarization at all. An asymmetric explosion, on the other hand, one that is symmetrical along one axis, like a football or a peanut-shaped explosion, would polarize light in a specific pattern. FORS 2 can help scientists decode this pattern. When light enters the instrument, it first passes through a rotating crystal plate that can shift the orientation of the polarized light by a precise amount. By moving this plate to different angles, The instrument effectively rotates any polarized light, allowing it to measure polarization in all directions. Next, the light hits a Wollaston prism, a unique optical component which physically separates the incoming beam of light based on the polarization direction. Light waves vibrating in one plane go one way, waves vibrating perpendicular to that go the other way. Each beam is then split into its component colors, creating two side-by-side spectra on the detector, one for each polarization orientation. By comparing how bright each wavelength is across the two spectra, astronomers can determine how strongly the light is polarized and in which direction. Knowing how the light from SN 2024 GGI is polarized tells us the shape of its explosion. From there, we can predict the mechanism that caused it. For over 50 years, scientists have tried to explain the physical processes that revive a stalled shockwave and trigger a supernova explosion. From the creative rubble emerged two leading ideas. The first says that neutrinos must have something to do with it. We know the core collapse sends huge amounts of neutrinos shooting into space, but in the incredibly dense region just above the neutron star, even neutrinos have trouble getting through. It's thought a tiny fraction of them deposit their energy into the material above the core, heating it from below. This creates a violent convection. If enough energy accumulates, the shock surges back to life, and the star literally blows its top, exploding furiously. But here's the thing, the convection doesn't heat the neutrinos evenly. State-of-the-art 3D simulations led by Bernard Müller at Monash University show these explosions are highly asymmetric, and we've observed real supernovae that fit this model well. The Cassiopeia A supernova remnant, for example, shows an asymmetric distribution of radioactive chemicals like titanium-44 and nickel-56, which trace back to asymmetries present from the onset of the explosion. The second theory says jets are behind the boom instead. The collapsing core forms a rapidly rotating neutron star surrounded by a disk of infalling material. Magnetic fields threading through this disk get wound up and amplified by the rotation, twisted tighter and tighter like a rubber band. These amplified magnetic fields channel material into two powerful jets shooting out along the star's rotation axis like cosmic blowtorches. They punch through the star's envelope with tremendous force, driving a fundamentally different explosion. In this scenario, the blast would produce axial symmetry along the star's spin. The explosion then expands along this axis, leading to a football-shaped or olive-shaped geometry. We've seen this kind of structure in other supernovae like SN 2023 IXF, whose explosion was also organized and elongated. So what do you think Yang's VLT observations show for SN 2024 GGI? Pause the video and comment below. An explosion if you think it's highly irregular and asymmetric like the neutrino-driven model predicts, or an American football if you think it's symmetrical along an axis like the jet model predicts. So, moment of truth, this is what SN 2024 GGI looked like. The spectropolarimetry data collected by the VLT's FORS-2 revealed a clear, well-defined axis of symmetry and an olive or football-shaped explosion, technically a prolate ellipsoid. At first, it seemed like a clear win for the jet-driven theory. If the explosion were driven by neutrinos, it would have been completely asymmetrical. Finally, we had the conclusive, observational data we'd always been missing. Case closed, right? If only it were that simple. These models are based on simulations, theoretical physics, and extrapolated information from supernovae we caught much later, after the critical breakout phase window shut. The neutrino-based model certainly has its shortcomings. A 2015 article from the Royal Astronomical Society showed that 3D neutrino-driven simulations produce explosions an entire order of magnitude less than what we've seen observationally, even in the most favorable of conditions. This suggests neutrino heating alone simply isn't enough to explain the blast. But the jet-driven theories aren't flawless either. 2D models seemingly work well, but when astrophysicists simulate jet-driven explosions in 3D, something strange happens. A team at Caltech introduced a 1% wobble around the axis of symmetry of a rapidly rotating magnetized stellar core. That tiny change made the jets unstable. They twisted and kinked, winding around the rotation axis like water streaming out from a garden hose left lying on the ground. Instead of punching cleanly through the star and driving an explosion, the jets produced two misshapen lobes of twisted, highly magnetized material that slowly pushed outward. The explosion never happened. There simply wasn't enough energy to trigger an explosion. Yet SN 2024 GGI clearly exploded. So there must be something else going on. Either our models are incomplete, or we've missed something else entirely. The solution might lie in flipping the old theory on its head. What if the fatal wobbling and kinking is actually an essential part of the explosion? If jets rapidly jitter rather than maintain a stable axis, they can't drill a clean channel through the star like in the classic jet-driven model. Instead, they're forced to deposit their energy close to the core, roughly 1,000 kilometers from the center, through shock waves. These shock waves create hot, pressurized bubbles that merge and expand, pushing the stellar material outward and driving the explosion. The jets themselves are chaotic and unstable, but the overall explosion geometry remains axially symmetric, just like SN 2024 GGI. So, where does this leave us? Well, SN 2024 GGI definitely showed us that explosions can have organized axial symmetry, and how it arises, whether through narrow jittering jets or a magneto-rotational mechanism or something else, remains a mystery. We're still unsure what role neutrinos play in explosions like this, if any. It also raises questions about alternative mechanisms that could cause asymmetrical supernovae like Cassiopeia A and others which don't follow axial symmetry. Are they in fact caused by neutrinos or something else? Which factors determine what kind of explosion occurs? This might come as a shock, but we can't know without more data. SN 2024 GGI is the only breakout phase we've observed in such detail and measured in real time. If we could somehow know when and where supernovae were going to explode, we could make a point to track them all and look for the patterns. And that's exactly what researchers plan to do, thanks to new full sky surveys like ATLAS becoming increasingly popular. 2025 alone saw the inauguration of the Vera C. Rubin Observatory Legacy Survey of Space and Time, NASA's Sphere-X, and the latest data release of the Sloan Digital Sky Survey. Astronomers are optimistic that with these new tools, they'll be able to regularly catch supernovae within 24 hours of explosion. If they notice an object is absent from previous night's images, but then appears within a galaxy, they'll follow up immediately with spectroscopy to determine the object's characteristics as fast as possible. As more automated survey systems come online worldwide, our ability to catch transient events in their earliest moments will only continue to improve. SN 2024 GGI showed us our models aren't quite there yet. The next generation of observations should help us find the missing piece and solidify our understanding of how stars all over the universe draw their final breath. And I mean, who wouldn't want to see more supernovae getting caught in their explosive moments? A 90-year-old cosmological cold case may finally have been solved. For decades, there was a silent operator lurking in the shadows of the universe, one that doesn't emit light or reflect it, one that our telescopes can't see, despite the fact that there is 6 times more of it than there is of the regular matter that makes up you and me. What I'm talking about, of course, is dark matter. It's fundamental to our models of the universe, and yet we still don't have a clue what it is. Physicists across the globe are using state-of-the-art particle accelerators, underground laboratories and telescopes in an attempt to detect direct evidence of this elusive matter, with zero success. But in November 2025, a paper was published that rocked the scientific community. Whilst trawling old data from the Fermi telescope, a researcher may have finally captured a glimpse, a telltale signature coming from inside the Milky Way. But how can we be sure it's dark matter producing this signal? And will this mystery finally help us explain what dark matter is after all this time? I'm Alex McColgan, and you're watching Astrum. Join me today as we probe this juicy new lead and answer the question that I know you're all thinking: did we just see dark matter? This is Fritz Zwicky, a Swiss astronomer born in 1898, who spent most of his life working at the California Institute of Technology in the United States of America. His time at Caltech began as part of a research group studying the physics of crystal structure, but he was soon swept up in the exciting, newly emerging field of cosmology. Probing the mysteries of the cosmos became Zwicky's passion, and while he was well known for having an eccentric personality, his biggest legacies were his discoveries. His research into the origin of cosmic rays led to his conceptualization and coining of the term supernova. He catalogued tens of thousands of galaxies, and over the span of his career, published hundreds of papers on a wide array of astronomical subjects. But despite all this, he is best known as the father of dark matter. In 1933, aged 35, Zwicky was measuring the redshift of galaxies using the Mount Wilson telescope, the very same that Edwin Hubble had used to prove our universe was expanding just a few years before. Redshift is a phenomenon whereby the light from a distant object is stretched on its journey from source to observer. The more it's stretched, the longer the wavelength becomes, and the redder the light appears. This indicates that the source is moving away. Zeroing in on a small patch of sky in the Coma Berenices constellation near the Milky Way's North Pole, Zwicky spotted something incredible. Galaxies within the Coma cluster were traveling at speeds that seemed impossible given the commonly accepted laws of physics. Sitting at his desk, he began to calculate the difference in velocities between 8 of the galaxies. It was more than 2,000 kilometers per second. These galaxies were traveling at such high speeds that this cluster should have ripped itself limb from limb long ago. How could what he was seeing with his very eyes be reconciled with the figures on the page? Calculating the mass of the cluster, Zwicky realized that the gravitational pull of the stars and gas alone was not strong enough to stop the galaxies from escaping one another. In fact, he worked out that the system needed around 10 times more mass than had been observed just to stay together. He concluded that something more must be at work, something dark, enough to be concealed from view, lurking deep within the cluster to anchor these galaxies in orbit. What was this dark matter? The question of dark matter's true identity has continued to plague cosmologists since Zwicky's study on the Coma cluster over 90 years ago. Dark matter was so called because of its very nature. This is a substance that doesn't interact with light. This is a problem because light is the primary tool we use to probe our universe and understand how it works, from the micro to the macro. Dark matter doesn't emit light, nor reflect it, and it doesn't even absorb light to cast a shadow. So it is truly invisible. And like Zwicky, we instead have to observe its ghostly effect on objects that are visible to us in order to perceive its presence. We know dark matter is there, and that it exerts a gravitational force on visible matter, but we don't actually know what dark matter is. The two leading theories today are WIMPs and axions, though we've not yet found hard evidence for either of them, until November 2025 that is, when that news erupted from the University of Tokyo. Astrophysicist Dr. Tomonori Totani had found a signal never identified before emanating from the Milky Way, and it appeared to have the properties of being produced by WIMPs. Was this the first observational evidence of dark matter? To answer this question, we need to understand the nature of a WIMP. No, we don't think they are particularly shy or cowardly creatures, but they have been highly successful in evading our detection so far. This is a class of particles predicted to exist within an extension of the standard model of particle physics known as supersymmetry. WIMPs, being weakly interacting, neither absorb nor emit light, and they very rarely interact with other particles other than through gravitational attraction, which ticks many of the boxes we're looking for when it comes to searching for dark matter. These properties also make them very challenging to observe. However, there is a way in which we should be able to detect the presence of WIMPs, and this is through a process called annihilation. In the standard model, all particles have an antiparticle pair. For example, the proton has its antimatter counterpart, an antiproton. Both the proton and antiproton have the same mass, but possess an equal and opposing electric charge. Another example is the negatively charged electron, whose pair is the positively charged positron. You might not realize it, but antimatter is everywhere. It's even emitted by your regular banana. When a particle meets its antiparticle, they cancel each other out and annihilate, releasing a signature burst of radiation, often in the form of photons and gamma rays. The energy profile of those gamma rays can be measured and is related to the mass of the original particles. We believe the mass of a WIMP to be between 10 and thousands of times that of a proton. Yes, that's quite the range, and the resulting gamma rays would have a corresponding energy signature. If another eccentric physicist by the name of Albert Einstein is coming to mind for you right now, you'd be correct to make this connection. Einstein's famous equation E=mc² revealed that mass and energy are interchangeable, and the annihilation of a pair of particles is the most beautiful and fundamental example of this formula in action. Anyway, back to dark matter. Gamma rays are incredibly helpful clues for astronomers. Like fingerprints left at a crime scene, they indicate where activity has occurred in a region of the galaxy, and where it may be pertinent to take a closer look. However, both gamma rays and fingerprints can be left by a myriad of different sources, which creates a serious issue. Gamma rays are created and released in all sorts of astrophysical processes, from the hot accretion disks around black holes to the death throes of a dying star. So how can we detect the true signal of dark matter, if it is the annihilation of WIMPs, in such a maelstrom? Well, it takes a new and honestly quite painstaking approach. In early 2024, Dr. Totani began dredging through the Fermi telescope's enormous back catalogue for clues in solving this dark matter conundrum. The gravitational geography of our galaxy dictates that the majority of visible matter is concentrated in the galactic plane. From the outer tendrils of the spiral arms to the densely packed galactic center, all manner of stars, planets, and our behemoth supermassive black hole, Sagittarius A star, make up our home galaxy. Naturally, this means that the majority of sources of high-energy radiation, that is, gamma rays, are located in the plane too. But when we observe the movement of stars and gas around the galaxy, this indicates that the dark matter has a different shape. It is not concentrated in the galactic plane as we might expect, but it extends around the Milky Way in a sphere structure termed the halo. By scraping 15 years worth of Fermi data and blocking out the blinding gamma-ray rich center of the galaxy from his study, Dr. Totani has been able to diligently remove known astrophysical producers of gamma rays from the background source by source. What was left has floored the scientific community and me. Honestly, this is so exciting. A unique pattern of gamma rays in the ghostly shape of the Milky Way's predicted dark matter halo. But Dr. Totani's research takes this theory another step further. Not only were these gamma rays revealed to be populating the correct shape and structure to be the dark matter halo, but they had an energy spectrum peaking at 20 giga-electron volts. This is in the suitable range to be caused by WIMP annihilation. If this gamma ray signal is from WIMPs, it cannot be underestimated. This observation will have changed the face of physics forever. But before we can be absolutely sure, there are still a few puzzling parts of this case to solve. Firstly, we're still getting to grips with exactly how much mass WIMPs do have, and therefore the energy signature expected to be produced during annihilation. After all, they are still only theoretical particles. And while teams at particle accelerators around the world continue to have success in constraining their properties, we're so far limited in working with the rather wide range I mentioned earlier. There are also concerns over the population density of WIMPs required to produce an annihilation signal as strong as the one measured in Dr. Totani's study. WIMPs are relics created from particles present at the Big Bang, and by studying the early universe through evidence like the cosmic microwave background, we have a good sense of the numbers of each particle we expect to be populating the universe today. The signal seems like a much denser collection of WIMPs than we would expect to be possible from this evidence and particle physics models thus far. But this field of research is one that can't afford to ignore new leads. And right now, WIMP annihilation, and therefore dark matter, is a strong contender for what this gamma ray signal might be. Some even argue the strongest. But given we've never seen a WIMP, many are erring on the side of caution. Professor Carlos Frank, a lifetime researcher of dark matter and one of the originators of the leading cold dark matter theory, including WIMPs, has likened finding the source of dark matter in significance to humanity as Charles Darwin's theory of evolution. It's not something you claim to have found unless you really are sure. So scientists are excitedly working to help better determine the factors that could be at play in Totani's signal so that they can untangle the snags and gain a more definitive answer. One thing is for sure though, the more we discover at the Rubicon of this fantastical microworld of quantum and particle physics, and the vast expanse of cosmology and general relativity, the closer we get to solving the biggest mystery of our universe in unifying the two. So, is this enough to lay this cold case to rest? Unfortunately, not yet. While this is brilliant new evidence, and a well-needed re-injection of energy in what has been a relatively stale search for dark matter of late, there is still more work to do before we can close the case file on WIMPs. If WIMPs really are at work here, we would expect to see similar gamma ray signals in our dwarf galaxy neighbors and beyond. So, what can we do next? The latest investigator on the scene is the new Vera Rubin Observatory in Chile. Vera Rubin was a prolific researcher in the field of dark matter. In the 1970s, she discovered the effect of dark matter on the velocities of individual star populations in over 60 galaxies, and it was Vera's work on categorizing these effects that brought serious consideration to the theory for the first time. This was a pivotal moment in convincing the scientific community that dark matter was real and a valuable thing to study. The observatory of her namesake came online in June 2025, and datasets from the first schedule of observing are expected for release in 2026. Through taking hundreds of images of the southern hemisphere sky each night, amounting to 20 terabytes of data, or the equivalent of 78 standard iPhone 17s, the Rubin Observatory hopes to uncover objects never before seen in our night sky. At the end of the first 10-year survey, This raw image data is expected to sum up to more than 60 petabytes, or 60 million gigabytes, in a monster effort to reveal the secrets of our universe. Dark matter makes up more than 80% of all the matter we know, and it is fundamental to the very fabric of our existence. Its gravitational influence enabled the formation of the first baby stars and galaxies at the cosmic dawn. It sculpted our cosmos to look the way it does today, and dark matter will continue to influence the fate of our future too. This new study, presenting the first indications of the presence of WIMPs in our galaxy, is the most exciting development in the observational search for dark matter for decades. I can't wait to see the fresh research that stems from it. In Switzerland and South Dakota, from Chile to low Earth orbit, brilliant human minds are on the case to find the true nature of dark matter, elusive WIMPs or not. So stay tuned, because we might just be on the cusp of a dark revolution. And isn't it a thrill to watch it unfold? There's a reason these educational mini documentaries are free for everyone. It's not just the ads or sponsors, but it's thanks to our hundreds of Patreon members who make it possible for everyone to get the best possible content. They are the foundation that keeps Astrum steady and focused on quality over clicks. Every video you watch exists because there's a community behind it that values learning and curiosity. If you'd like to be part of that group, the people who keep space education open to everyone, join us on Patreon through the link below. We would love to have you.